Okay. Write a general MATLAB function to determine the numerical solution of a two-dimensional elliptic partial differential equation of the general form as such for a rectangular object of variable width and height. The object could have Dirichlet, Newman, or Robin's boundary conditions. The value of f should be assumed to be a constant. Use this function to find the solution of the following problems. Okay. Now, um, the Dirichlet boundary conditions is it specifies the value of the function on the surface, okay? Whereas Newman boundary conditions specify the normal derivative of the function on a surface, whereas Robin boundary conditions, okay, for an elliptic partial differential equation in a region, Robin boundary conditions specify the sum of um, AU and the normal derivative U equals to F at all points of the boundary conditions with A, alpha, and F being prescribed. Okay, so we'll look into the question here. A thin square metal plate of dimension 1 to 1 meter is subjected to 4 heat sources which maintain the temperature on its 4 edges as follows. Okay. The flat sides of the plate are insulated so that no heat is transferred through these sides. Calculate the temperature profiles within the plate. Right. So the second problem is perfect insulation is installed on two edges of the plate of part A. The other two edges are maintained at constant temperatures. The set of Dirichlet and Newman boundary condition is, so this is your Dirichlet boundary condition and this is your Newman boundary condition in which it has a function. Okay. Calculate the temperature profiles as well within the plate and compare these with the results of part A. The tin metal plate of part A is made of a tin alloy that has a melting point of 800 degrees Celsius and a thermal conductivity of 16 watt per meter per Kelvin. The plate is subject to an electric current that creates a uniform heat source within the plate. The amount of heat generated is 100 kilowatt per meter cube. All 4 edges of the plate are in contact with a fluid at 25 degrees Celsius. The set of Robin's boundary condition is given as such. So examine the temperature profiles within the plate to ascertain whether the alloy will begin to melt under these conditions. So, so we open our MATLAB, right? So I've already put in the M file. So you save it in your MATLAB file. Okay. So over here, this is what it will display. And this is what we have to key in, the boundary conditions. And over here, we have to input the length and the width of the plate, the number of divisions in the x direction and y direction, as well as the right hand side of the equation in the boundary condition. And then we have to choose which type of boundary conditions it is. Okay. So then we will click run. Okay, you should have a figure popping out here. So the length of the plate is 1 meter. Width of the plate is 1 meter as well. Number of division, you can put 20, 50, any number you like. I put 20. The right hand side of the equation is 0. So for your first boundary condition, which is your lower x boundary condition, it is a Dirichlet boundary condition. So we select 1, and the value was the value was 250 degrees Celsius. So these are the values that we put in here. Yeah, okay, so 250 16. Next, upper x boundary conditions. This is also a Dirichlet boundary condition in which the value is 100 degrees Celsius. Lower y is 1. Okay, Dirichlet also. And the value is 25 degrees Celsius, followed by the upper y boundary condition, which is, oh no, this is supposed to be, lower y is supposed to be 500. Okay, it's okay. Let's clear this. Okay, let's run it again. Sorry for my mistake. So it's 1 meter, 20, 20, this is 0. Okay, this is 1 and 250 degrees Celsius. This one is Dirichlet, 100 degrees Celsius. Dirichlet, 500 degrees Celsius on your lower y boundary condition. And 25 degrees Celsius. Okay, then you should get your temperature profile as such. Okay, then we can repeat the calculation. Okay, we want to calculate for part B, so we press 1. Okay, so for part B, same thing, the length of the plate is the same, which is 1, width is 1, 20 over here, and F is equals to 0. So the lower x boundary condition is a Dirichlet boundary condition. This is a Dirichlet boundary condition, whereas this is a Newman boundary condition. Okay, lower x is Dirichlet, whereby the value is 250. The upper x boundary condition is a Newman boundary condition in which the value is 0. Lower y is a Dirichlet with a 500 degrees Celsius value, and upper y is Newman with a value of 0. Okay, then we can see the temperature profile here. So it becomes different. So the effect of insulation on the right and top edges of the plate is pretty evident compared to part A. The gradient of the temperature near these boundaries approaches 0. Okay, to satisfy the imposed boundary conditions. Because the insulation stops the flow of heat through these boundaries, the temperature along the insulated edge is higher than that of part A. Okay. For the next one, okay, we repeat our calculation for part C. So for part C, the length of the pipe is the same. So it's the same, but your right hand side of the equation is 100 kilowatts. Okay. So we will put negative 100 E3 divided by 16. Okay, so this one is a Robin's boundary condition, which is 3. And your constant beta is negative 5 times 25. Okay, which is given here, negative 5 times 25. This is your beta. Okay, and whatever the value for this one is your gamma. Okay, so your gamma is 5 times this. Okay, 5 times this, so the gamma is supposed to be 5 because this is your U. Okay, gamma multiplied by U. So your gamma is 5. Enter. Your gamma is 5. Upper X, this one is also a Robbins. And for this one, okay, your gamma is -5, whereas your beta is 5 times 25. 5 times 25, gamma is 5 times U. Okay. Constant beta is 5. This one, -5. And same thing, 3. -5 times 25. Below y is -5 times 25. And your gamma is 5. This one is 3. 5 times 25 and -5. Okay. And then we'll check out the temperature profile. It becomes like such. So the Poisson equation is solved with a Poisson constant determined as follow, which is your F over here, okay, which is your 100, your Q divided by your K, okay, and the solution is shown here, your temperature profile, and it can be seen from this figure that the temperature within the plate rises sharply to its highest value. You can point over here to check the value of 824.9 degrees Celsius at the center point. It's a bit slow, right? And then under these circumstances, the metal will begin to melt at the center core because the question says that the maximum temperature is melting point of 800 degrees Celsius, right? So because over here it is 824.9 degrees Celsius, you can point over here to identify the value. Mine isn't working, it's a bit lagging. So it's very lagging. But when you point here, it will show you the value at that point. So you will get a highest value of 824.9 degrees Celsius at the center point here. So your metal will begin to melt at the center and increasing the heat removed from the edges by convection or by either lowering the fluid temperature or increasing the heat transfer coefficient can lower the internal temperature over here and prevent melting of the plate. Okay, so that's all for tutorial 6.